Thank you so much. Good evening, fellow MIT alums and Caltech over there, right? So tonight we're really honored to have Dennis White here from Course 22 to talk about fusion. And fusion is one of the ultimate, if not the ultimate, energy source. And there's a lot of people working on it in a lot of different areas. And we're going to hear about some really exciting stuff going on at the Institute. This, just to put things in perspective, in case you've forgotten, this is a little vial of 1 gram of D2O, that's deuterium oxide, and it's the equivalent of 10 tons of coal, and it would power a home for over a year, and it's equal to 18 megawatt hours of energy if you could get that just out of 1 gram. So that's the potential. And of course, we got a lot of water in the oceans, 70% of the surface of the planet. So it's my great honor to introduce Dennis White, who is the recently promoted head of the Nuclear Science and Engineering Department at MIT, and is also the director of the Physics, Science, and Fusion Center, the Plasma Science and Physics Center at the Institute. Dennis received his bachelor's degree from the University of Saskatchewan in 1986 and his master's of science from the University of Quebec in 89 and his PhD from the University of Quebec in 93. And after that, he went and worked. When you say appointment, is that teaching or research or both? Both, yeah, teaching and research at the D3 fusion facility at General Atomic in San Diego, and then was at the University of California in San Diego, and then off at University of Wisconsin, and then, the light bulb went off in 2006, and he came to the Institute. Good choice. And we're so excited to have him there. So, what's fascinating is that department heads are tenured, right? Yeah, so he's been at MIT, and he got tenure in 10 years. And pardon the pun, but it's really tough to get tenure at MIT. So this is really an accomplishment. And he's a department head. So this is a great guy. So he's a recognized leader in the field of nuclear fusion, with his research addressing the boundary plasma material interface in that area. Along the way, he's become a fellow of the American Physical Society Division of Plasma Physics. In 2003, he was awarded the Department of Energy's Plasma Physics Junior Faculty Award. 2011, he served on an NRC committee on the prospects for inertial confinement. 2013, he won the International Atomic Energy Agency's Nuclear Fusion Prize. Now, 10 years at MIT, twice he's received the MIT Joel and Ruth Spira Award for teaching excellence. So, what a great combination. Great research, great teaching. And again, in 2015, he got the National Science Foundation's Engineering Distinguished Lecturer Award. So, Dennis has also authored more than 300 publications. On the personal side, he's a great sports fanatic, right? Fair, yeah. A lot of golf, a lot of snorkeling and swimming. Played hockey in Canada, and his best friend playing hockey. Now, he was a goalie, but he still has all his teeth. You'll note, right? Right, smart too. And his best friend was a #1 NHL draftee, and went to play for the Bruins. So you can guess that his favorite hockey team is the Bruins. So I'll leave it at that, and let's have a round of a warm welcome for Dennis.
Well, thank you very much. Really an honor and a pleasure to be here today. I don't get to the West Coast much anymore. I used to be a California denizen. So what you're seeing here is, one of the first questions that people usually ask about fusion is like, when is it going to be real, right? When's it going to happen? Well, actually, fusion is actually real. This is what you're seeing is actually a pulse from our high-field torus at MIT on Albany Street, if you remember where that is reaching temperatures up to 100 million degrees in an object which is actually smaller than what you're seeing up on that screen. and it's making 100 trillion fusions a second. The science of fusion is real. What I'm going to try to tell you today is that there's an interesting pathway about getting to actually fusion energy, which is sort of what we're interested in. So, you'll see that was the title of this is Smaller and Sooner. It's about looking at new technologies that will accelerate fusion's development. And I will explain at the end of this what the subtitle means, Spark at the Park, which happened to be a very interesting confluence, I would say, of naming, but I'll get to what that means. And please note that this is a real team effort we have, and I'll talk about the people, in fact, we have at the Institute, including students. So the first sort of question in this is, it was fusion breakthrough is a question. So what are the breakthroughs that I'm going to talk about? So the 0th point I want to make is that we have had the basic science knowledge to make deuterium-tritium fusion energy gain for over 20 years. And I can tell you this because I can teach MIT undergraduates in about 3 lectures how to design a fusion reactor based on physics, just the physics of this. And this is using magnetic confinement. And our science has become quite strong, actually, but we actually stalled in our energy mission. And here's where the breakthroughs are. We actually have now available a new kind of superconducting material that allows us to double the steady-state magnetic field strength. This leads to a 10-fold reduction in the size of fusion energy devices. The second part of this is that we were able to design them with demountability. So this means that we can design modularity and actually have great easing of the nuclear technology, which is actually required for deuterium-tritium fusion. And perhaps the biggest one is actually that fusion devices that demonstrate energy gain, which is the holy grail of what we're going after, can become small enough that we can actually start to use a development model which is privately funded and is actually based on the rapid innovation cycle of startups. So it's more than just about a set of technology breakthroughs. What I call is sort of a attitude breakthrough about getting to a place that you're starting to build up success at a faster rate. So this is the usual place that you start. Of course, the universe has already told us the answer. Essentially, the reason we all sit here is because of nuclear fusion, which happens in the interior of stars. On Earth, we can't use this mechanism of stars, of course, to hold it, which is gravity. What we have instead is that we use a special kind of a special kind of hydrogen fuel, which is deuterium-tritium, and I'll get a little bit more to this. And you take a basic look at, in fact, the probabilities of these reactions happening. We measure these quite well versus the particle energy. You kind of speed these up, they slam into one another, and they make this fusion reaction that produces energy. In the end, though, we know that this needs confinement. It's because when you do the basic calculation of how fast the particles scatter off of one another rather than fuse, you find out that that's much larger, in fact, than what you could ever get the fusion rate to be. So you need to sort of hold this together. The stars do it by gravitation. And this is the basic thing, and this is where, as a nuclear engineer, this is the entire fuel cycle, actually, of a fusion power plant. There's a deuterium-tritium fusion, which is the kind of fusion I'm going to talk about. You can ask questions about the other ones afterwards. What this produces is helium and a neutron. The power balance is very simple. The energy which is released in this, which is about a factor of sort of 2,000 or 3,000 energy multiplication compared to the original starting energy of the deuterons and tritons, the energy of this helium, because it has charge on it, is actually coupled back through scattering into it. So that's the energy recycling. It's simply this hot energy helium particle basically heats that back up. Then we also produce a free neutron. The neutron escapes the system. This is how we get energy out of it. We actually make the neutron collide with a lithium atom, which in the surrounding materials. This actually makes the tritium. And the reason that this is so attractive is because in the end, even though this looks like the fuel is deuterium and tritium, it's not. The fuel is actually deuterium and lithium. And that's what we have down here, is that the end reaction is actually, what comes into the plant is deuterium and lithium. And you saw the vial that was put up by Larry, that not only is deuterium incredibly abundant on Earth, lithium is extremely abundant on Earth. So why is it the ultimate energy source? Well, the first one is that you basically have limitless fuel. The fuel that you can extract easily is actually hundreds of millions of years worth of fuel. So since that's past the time scale of human evolution, I'm not going to count that. We'll leave that to the next species. There's no radioactive fuel waste in the fuel cycle, and this is because what we do is recycle the neutrons in this, and our radioactive waste product is helium. And basically, because you do not need fissile material in place, the risk of proliferation is if not zero, is very close to it. It's inherently safe because it does not rely on a chain reaction. It actually has to happen at a temperature which is very high, which I'm going to do. It is intrinsically greenhouse gas free. And then here's the other important one, which is why we like nuclear energy in general. It has very high power density. You get millions of times the amount of power out per reaction or per unit mass, if you want to think of it that way. What this leads to is why standard nuclear power plants have very small environmental footprints. And fusion is actually in this way as too. And here's, I think, in some sense, the biggest one on the bottom. You can rapidly scale this to large fractions of your energy demand. So why do I say that? Because you're saying, well, you guys haven't actually made a fusion reactor yet. It's because we already did it with a kind of technology once, is with a light water reactor. So with a light water reactor, and this is actually what keeps motivating me, is that the very first joule of energy put on the grid by nuclear fission technology was just before 1960. And then what you saw was that on the time scale of sub-decade, you were talking about that it was producing something like over 10% of the United States electricity. And the reason for this is actually because of the basic feature of nuclear energy processes. You can make very large amounts of power in small objects, and the fuel is not limited, so you can deploy this very fast. And if you're looking to, in fact, take on climate change, that's actually an attractive feature of all nuclear energy sources, and fusion actually has this as well, too. So you can do it, but we also need to get going. In fact, I just plucked this up because literally I just said, what's the most recent article on Google about climate change? This was like yesterday. This is some atoll in Alaska, I believe. It's disappearing, actually. And you know, we don't actually have a lot of time, actually, to be deploying large-scale, low-carbon energy. So I'm just going to leave it at that. That seems like an obvious thing that we need to do. So how could fusion help with this? So now we get to about making fusion work. So if you say, this list all sounds so great, but how do you actually make it work? So you basically have 3 recipes that are very well established. I mean, the science of this was known like 50 plus years ago about what you need to make this an energy source. The first one is sort of obvious. You need gain. Namely, you need to make a lot more power from the fusion device than power that you have to put in to keep it going. You need fusion power density. That was particularly to what I just said before. Namely, you need to make a large amount of fusion power in a small unit size so it's fastly deployable and it's also economically viable. And then the third part is temperature. You basically need to make these 100 million degrees. That's roughly the temperature that you need. So the interesting part of this is that this is, even though all those things sounded easy, the cuckoo one sounds like the temperature that I just said, 100 million degrees. And in fact, that's the one we do like all the time. Okay? It's these ones we got to work on, which is the subject of this talk, actually. So what I'm mostly going to talk about is what we call toroidal magnetic confinement configurations. And what this uses, so how do you keep something hot? The way this is being kept hot is that we basically take sets of magnetic field lines, we loop them back around on themselves, so this it basically becomes a natural container because it makes the plasma particles, and the plasma means that's like the interiors of stars, that's when everything's very hot and ionized. The magnetic field traps those energetic particles, and we keep them in a circle around like this so that the magnetic fields wrap themselves around. So this is in the shape of a donut, also called a toroid, which you can see there. So this is the way a theorist would draw it. It's beautiful. This is the way an engineer would draw it. And so what we actually produce are very strong magnetic fields with using electromagnets. these are not your fridge magnetic fields. These are very high magnetic fields. And the way that you make very high magnetic fields is you take a circuit like this, you pass a current through it, you make a magnetic field. And note the general topology of this, because, and this comes from basic science considerations that we teach all the students, is that the confinement there is no confinement along the direction of the magnetic field. So this has to be actually closed into a loop that's like this. And in fact, it makes a helical shape of magnetic fields that wrap around on themselves. Because of that basic topology, the magnetic electromagnets actually have to totally surround. And that's going to play an important role afterwards in what we're going to talk about. So let's put some numbers on this. How do you get gain? Well, you can actually technically make this infinity. Okay, that means it just keeps itself hot, going all the time. This needs a requirement of basically a product of the pressure of the plasma. And here, when I say pressure, just think about like gas pressure. Okay, and in this tau E is just a consideration of how long the system holds its energy. It's just a time. Okay, so it's a simple number. It actually turns out to be 10 bar seconds or 10 atmosphere seconds. And the power density actually itself is then another, how much fusion you make per unit volume goes like the pressure of the plasma squared. So you multiply it by itself. So put those numbers together, and in fact, this is what makes fusion so attractive. This sounds so easy in some ways, okay? Well, again, this part was maybe not, it means that it has to be at 100 million degrees, which is what we achieve, by the way, in the center of our torus. Is only this far away from a mechanical object. That's because we're using the magnetic field to basically insulate it away from those surfaces. And then the other thing that you need is about when you have 10 bar of pressure, that makes about 10 million watts per cubic meter of plasma. So to put that into that's approaching basically what a standard fission power plant makes. So that's 10 million watts, or that's actually probably something like 20 million watts coming out of something the size of this podium here. That's power density. That's what you love about nuclear power. And so if you did the math right, you notice that if we want to get 10 bar, and I look at this one, this says that I have to hold the energy in for about 1 second. And if you do that, you got a fusion system ready to go. Okay, so have we done this? Well, to a point, yes. Like I said, we've done the 100 million degrees, and we've actually made real fusion power in the laboratory. And here's what happened. This is actually one from in the United States, which is actually I'm not going to show the details of this, but I'll just point up at the very top of this scale. This is power output of fusion from deuterium-tritium fusion. That's 10 million watts. We did it, okay? And that was done in about 1995. And in fact, this is a device bigger than the one that's at MIT, that's in the UK. And this also made about 10 million watts of fusion power. But it did not actually get net energy gain. It fell short of that. Okay, very interesting. So all of this, you say, so all of this very nice, you did very well, so what's happened? Well, in fact, this was a rapid deployment of the world scientific community about advancing, about how you put all of this together, this magnetic confinement system together. And here's a very interesting plot, because particularly for the audience here in Silicon Valley, this is actually the years from 1970 to 2000, so it's 30 years. And here's famous Moore's law about being able to double the amount of computing power that you have per unit area on this. Fusion was actually creaming Moore's law. And this is fusion energy per pulse, and this is rapidly going up. And in fact, there's 12 order of magnitude increase. So there was this this is my 0.0. We've done an enormous amount of advancement in the basic containment of how the plasma works. And here's, okay, but we've stalled. And we stalled, and maybe some of you have heard about the ITER project. It's actually I'll get a little bit more into this, is that's the last time we did it. It was 20 years ago. Boo. For something this big. And so what's going on? And the reason the message of the talk is, it's not the science that stalled, it was the technology and the size. The size of the device got so large that it basically is impeding the progress, the rate of progress that we want to see. And that's actually, here's ITER, okay? there's the person beside it. Can you see the little blue person right beside it, right there? Yeah, yeah. Okay, so, and ooh, yeah. Now, ITER is a science experiment, which was, this is how, how well we believe in the science, is that the world's governments were willing to put up the money for this. It will get 10 times more fusion power than it takes to go. It actually doesn't quite get to that 10 bar one. It actually doesn't make its own fuel, and it actually doesn't make electricity. It's still a science experiment to show about what happens when you get gain and when the plasma starts to heat itself. But you get, just by your visceral reaction, it's big, right? It's quite large. And in fact, what it really is that it's taking the largest superconducting magnet coils ever produced by mankind to actually put this together. And this is one of the reasons why it's taking a long time for it to be put together. So what I like to do, because particularly I come from the Nuclear Science and Engineering Department, go back and look at history. And I showed you that plot about fission's development. And I asked myself one day, I said, how come those guys made it work and we're failing? Because I see, we still produce, 15 to 20% of the United States electricity comes from that design, basically a 50-year-old design. 75 to 80% of France's electricity comes from that design. Why are we failing in fusion? Because we've got all those other awesome features that everybody loves, right? And it was too big. ITER is a great science experiment, but it's actually too large. And because I went back and looked at the shipping port pilot in the fission plant. Those who come from Course 22 know what shipping port was. It was basically the pilot plant that Admiral Rickover designed. It had a volume under 100 cubic meters. It still cost a pretty penny, but it was under $1 billion in today's money, actually. And it only took 3.5 years from breaking ground to putting energy on the grid. That's the time scale that you want. So ITER is interesting. It's actually 30 times the volume, actually, of shipping port. And it's actually taking about that much longer to, in fact, put together, 10 times longer. But it actually costs the same about per unit volume. So it's actually not its cost, it's its time scale, which is actually slowing us down. So what's interesting is that JET, a device that we built already, it took about 3 to 4 years to build it, is actually about the right size. This is this tokamak, actually presently existing in the United Kingdom. But it only made 10 megawatts of fusion power and didn't get net energy gain. So it wasn't quite there. So now I come to the breakthroughs. We don't have to do that anymore, because now we've got a completely new way to make the magnetic field that is producing that confinement, and that's actually the Rebco superconductors. So why do we need that? So let's do a little science lesson in this first, is that when you fix the size, we want to keep it small. The magnetic field strength dictates both the plasma stability, confinement, and rate of fusion power. So you can think of almost what we're doing in that cartoon is that when you put this thing together at 100 million degrees, it doesn't want to stay there. It wants to push out. And the way that we basically stabilize against that is literally with a force. It's the magnetic pressure. So magnetic fields exert a pressure proportional to B squared, if you remember your E and M. And that's actually pushing back against this to hold the whole thing in. That's actually what we're doing. That's why we make these big magnetic fields. And the other simple one is the way you contain it. So when you put these very hot particles that have a charge, that's what they have, is the plasma, so that they spiral around the magnetic field. As you increase the size of the magnetic field, the size of that spiral keeps decreasing. And what really counts in this is then the ratio, in fact, of that size of that spiral to the overall dimensions of the device. So if I can double the magnetic field, I can shrink that spiraling size, and I can shrink down the size. And that's actually, so you can do the math, and I got some equations on here. There won't be a quiz afterwards, don't worry. No P-sets afterwards, you guys passed already. So the way to do this is the way to decrease fusion size is to make higher magnetic field. And now this is basically those same concepts that I showed you before, but just doing the math a little bit more carefully. And what you come up with is that and we're not going to worry about the things in blue. Those are things that plasma physics guys love, including me, but I'm not going to talk about those. R is the linear size of the device. So that's how far across it is. And B is the strength of the magnetic field. So if you have a choice in here, and in particular look at power density, which one of those two do you want to increase? When it's B to the 4th power. And note, in fact, that when you increase R, your costs go like R cubed, because that's the volume of the device. So look, all of this is very well known, and we did it. So what happened? So this is exactly what happened, is that when it came to make ITER, which basically uses superconductors to make the magnetic field, because it takes too much power to make this with copper magnets, is that ITER, the people who made ITER, including myself, because I have been through my career, and some of those prizes that Larry mentioned were about research on ITER. It's an interesting experiment, okay? But you are forced to build actually something this big. It's because you can't access magnetic fields past into this gray area. So if you look at basically reaching energy gain, and if you come to MIT, if you're a student, you'll know how to calculate all this. You basically make these contour plots. Here's energy gain. This is where you need to get to for a reactor. You actually have to make it at a major radius, which is very large, 7 to 8 meters. And that means that at that scale, it takes all the world's nations putting their resources together to actually build it, okay? But we've built a whole bunch of other devices, including the ones, for instance, at MIT. They're down here, but they can't actually access that high gain, okay? And so right now, here's our problem. All of our fusion eggs are in this one huge, slow, and politically fragile basket. Our political, this is being funded by governments. They're becoming quite, they're not happy about the delays in it, and it's costing a lot of money, and people really, like the reason you fill up this room, people really want fusion energy. But we need it, I think it looks like faster than this. So I'm not against ITER, I think we just need more options on the table. So what do we have? We have a revolution in superconductors. So this is, and by the way, so I'll start passing these out. Okay. So this is it. It's actually, it doesn't look like much, I know, but you can pass this around. So this is the superconductor. We don't make these. This is commercially available superconductor. It's just that I'm going to just pass these around in each of the segments, and I'll pass. I've got only 3 left because they took all of mine at Berkeley this morning. So what's going on in this? So it turns out that a superconductor means it has no electrical resistivity, which you all know. Is that another feature of superconductors is that if you keep increasing the magnetic field, then the allowed current that you can have in it, by the old kinds of superconductors, which is this black curve up here, exponentially decreases as you go to high magnetic field. So when you make a coil, what you do is you take the conductor, you put it in a circle, and you make current go through the coil. So the more current, the more magnetic field that you get. And what happens is that if you consider this on this plot, with a coil, you basically go on trajectories of straight lines, which are kind of like our little arcs that look like this. And when you hit this wall, of the current collapsing, you can't go any further, because the thing will cease to become a superconductor. And so then you're back to, it'll consume enormous amounts of electricity. This is the miracle, actually, of these new superconductors. They basically have, this is the red curve. That's what you're holding in your hand, by the way, is that to very high strengths of magnetic fields, there's no degradation of the current that they can carry versus magnetic field. It's still not understood about why that's true, actually, and there's some basic ones to it. So what does this all mean? And what it really means is that we can just blow right through this wall that was there before. And that's the wall that ITER hit. That's why its magnetic field is not strong, because it had to use this previous technology. And what we're looking at doing is doubling the magnetic field up here. And in fact, our analysis actually says it's not the superconductor anymore. It's actually the structural stress actually in the superconducting magnet. And that's actually where we end up, is ARC. ARC, affordable, robust, compact. Although if you watch Iron Man movies, you might also recognize the name. That's what happened. Hey, look, the student. So I want to point out, first of all, about who did this work. That's a graduate student. And in fact, this was a design class, 2263. That was a dozen really great MIT graduate students, and I basically gave them impossible problems, and they kept solving them, so I kept throwing them more impossible problems. And what I did is I more or less threw on the table this new technology and said, let's find out what a fusion device looks like when you put in this new technology. And this is what it looks like. So let's get to so you can see the person beside it. This is not quite the behemoth that it was before. There's minimum sizes that come with any nuclear technology, which I can explain. So what does this do? It actually produces more fusion power than ITER. And it actually makes 200 million watts of net electricity from the design. And I'll explain about why that is. And you can see here the person standing beside it, and what this is showing is actually the integrated engineering design. Almost none of this is in fact that superconductor. This is basically a whole bunch of steel. And it's less than 1% of this is in fact that superconducting tape that I just passed around. That's how amazing that superconductor material is. And so what is the science behind this? And this is why I get excited, is because fusion has been speculative in some sense, and I said we had the science. We actually already made 10 million watts of fusion power. This actually turns out to be almost exactly the size of JET, where we really made 10 million watts of fusion power. And you multiply by b to the fourth, which, trust me, is the right scaling in this, and you actually end up at 500 million watts. And sometimes I could almost end the talk there and say, look, we already did that science. We make the magnetic field 3 times as big as we did in this copper device in the United Kingdom. We've got 500 million watts of fusion power. Oh, good, okay. You know what? But that's still a science experiment, because we're going to keep going. Because we're going to keep going in the engineering and actually see about what this really means. So you can see by how simple that is, actually. And it doesn't even look like this looks like a piece of copper. What it is actually, really, literally, most of it is just steel coated with copper. It's Hastel, which is high-strength stainless steel, coated with copper. The most amazing thing about that is that thing that you're carrying around can carry over 1,000 amps of current, dissipation-free. And the current is being carried in a 1-micron layer in the middle of that. It's at 1/100th the thickness of that. And so what is so great about this is that not only is it an amazing superconductor, but just how simple this is structurally. It's basically a strong piece of stainless steel cable with copper coating on it structurally. So what this means is you can bend it. By the way, you try to you bend it, you can around. It's absolutely fine. It's extremely strong in tension. And you compare this to actually old superconducting technology, which was, by the way, invented at MIT and back in the day. It's just a complete game changer, because in terms of the complexity, or complexity to simple, in fact, about how you consider making the superconducting coils. This is an interesting area, too, because this is being driven now by American industry, a lot of it, that, in fact, these tapes have, in fact, improved every year, and they're getting better. So such that what this really means, I can make my device cheaper because I have to buy less tape. And this is actually another, again, a logarithm plot. That point over there is actually our design window for ARC. It's about a 20 Tesla magnetic field. And what you can, and these plots going up, which is in a logarithm plot, are basically kind of like each year, and they're kind of going up. They've improved almost a factor of 10 to the worst performance, actually, of the tape. It turns out when the magnetic field is going normal to the surface of the tape. So the way that we design is actually even got higher performance, in fact, than that. So this is what is, in fact, enabling to this. And in fact, when we started the design, our numbers were, in fact, down here. Now they're up here. So in fact, our design is already out of date, because we already put the margin in for that, and we would just have to buy less tape, which is good. So let's talk about making coils from this. So this is also another really interesting one. So let's go back to basic E&M. How do you make a magnetic field coil? Well, this depends on the number of ampere turns. I know everybody's starting to pull their hair. Oh my God, E&M. Oh my God. What is it? 802, I guess, right? So the way you make the magnetic field coil is that you take conductor, you wrap it around, and what you do is you take a small amount of total current per conductor, and you make it go around and around and around, and this builds up, and you make your magnetic field. This is the way all magnetic coils are made. So what you have to do, of course, is put an insulator in between each round of those, because the current has to follow one path, and then the next path, and then the next path. So a bright postdoc, actually, at MIT said, well, okay, what happens when I wind these? What if I just don't use an insulator? Because the stainless steel is the insulator. Because when I actually wind this and make it cold, all the current will carry in that one little micron layer, and then this turn-to-turn insulation is actually the stainless steel itself. So I literally now take that tape, about 100 meters of it, and 2 guys in a garage start like, it's 2 MIT guys, and it's not really a garage, but okay, that's close enough. They start winding this around, and in fact, this is what it looks like. So what is this? What is the benefit of this? It's obviously very simple. You get very large mechanical strength. You actually get enhanced radiation resistance, because it turns out that the way that most coils fail is the insulators fail, because they're ceramics, and they're very sensitive, in fact, to radiation damage. So what did this mean? So in the span of, because the tapes improved, because of our In fact, it was one of these considerations where you had to sort of do a data dump about the way that you make high-strength magnetic coils is you do this, you do that, but that was the old technology. The new technology, you make it a completely different way. And it's, again, here's the guys in the garage, they built this. And in fact, it was one of our MIT colleagues with collaborators from South Korea. They put this together, it's a stack of tapes, and in the span of 3 weeks, they broke the world record for magnetic field, actually, in a superconducting coil. So 26.5 Tesla. And now that probably doesn't, we'll get back to about what that means, okay? Just incredibly impressive. And if there's any superconducting and magnet nerds, I'd love to talk more in details because it's fascinating. So what does this mean? Like, how real is this technology to what we designed? We did this first, ARC. And I'll just point out the local parameters in this is that this actually, in the laboratory, basically meets or exceeds already what we designed in ARC. It's got a higher magnetic field. It's got the same local internal current density. Ours is actually easier because we don't actually have to cool it to 4 Kelvin above zero. This actually uses a different, I'll get to that. Uses the same materials. It's got the same internal stresses. Just the one slight difference is that this is made with a bore in the coil, which is about this big, and we have to make something which is meters big. So that geometry difference still resides in there. So what do you do? So this is actually showing you that, in fact, rather ordinary stainless steel structural materials can actually handle. This is the one challenge, which in fact is one of the expertise of our research group at MIT, is the one price you pay about going to high magnetic field is that the same thing that is pushing against the plasma is trying to push the coil apart. So you have to build it very, very sturdily. And this means you have to be clever about the mechanical engineering, basically, of how you put this together. So we were clever about the way you put this together. And in fact, we got it such that standard cryogenic stainless steels can, in fact, take the stress. It's still a pretty serious stress. It's about 500 atmospheres of pressure. So it's still, it's pretty impressive. But in fact, the materials can take it, which I showed you, because that coil that I just showed you before was actually at the same stress as this, okay? 5,000, thank you, yes. I knew that in the moment I said that. Yes, because it's not in Pascal, not in bars. So what is the ARC conceptual design? The other aspect of the high field is it gives you very stable operating scenarios. So what do I mean by this? So it's like when you design these toroidal systems, this is one of the science things we've studied. There's limits as to how hard you can make the press against the plasma, how unstable it gets, and so forth. So I'm not going to go into any of the details of that, except to look over here again at our gain equation. What people have had to have done to design fusion devices at the old magnetic fields is that they basically have to take enormous risk in the physics. And this is the risk. In fact, this Ares AT was a US-wide led design by the leading scientists in the US fusion program. And in order to get a fusion reactor to be economical, they basically had to operate it at every single limit of the device and above some of them. And that's just what this pentagram is these limits that we've established actually over the years. So I can be generous about being up against one limit perhaps, but not against 5 simultaneously. And we tried really hard actually to see if we could get all these simultaneously. We're not even close in the laboratory. And it's just we're not much smarter than them. We just solved it another way. Magnetic field strength, V cubed. And the other part of this is that, in fact, you talked about D3D and the device we have at MIT. The scenarios that we're using, and I'm not going to go into the details of it, the integrated physics scenarios have actually already been demonstrated in real experiments of the physics parameters, the normalized physics parameter. What this means is that what you're really doing is retiring large fraction of the science risk about going forward with fusion, with this particular kind of fusion. This is what makes it so attractive about near-term applicability. And it's even more subtle than that. In fact, this is really one of the things we've studied at MIT, is that there's other things that come in terms of benefits, particularly when you make the magnetic field very high. It basically starts to tame just all of the whole suite of plasma instabilities that exist. And when that happens, it actually turns out that this is very advantageous to that confinement that I was talking about. This is actually what we won the Nuclear Fusion Prize for, actually, in 2013. We found that when we tamed these instabilities sufficiently and did it at a very high magnetic field, and it turns out this only really occurs at like the magnetic fields we make at MIT, is that the plasma all of a sudden magically just held in its energy by a factor of 2 better than it did before. It's not magic, it's actually science, but it seems almost like magic when you do it. So it turns out that there's this whole host of other things, and I could go, it's lectures and lectures of why this approach actually has low science risk. So that's actually and in some sense, in many ways, it's a story we've known for a long time. If you can increase the magnetic field, make the device much smaller, make it much more stable, all very good. There's more to it than that, though. And this really comes down to modularity, economics, and engineering. So remember that basic feature of our toroid that has to be looped together, okay? So if you now have to take out the interior bits, there has to be a bit inside that is right up beside the star. You saw the original picture. All of those bits inside are up beside a thermonuclear plasma. They get worn. And that's actually my own area of research. They get worn really fast, in fact, if you don't take care. But they still have a finite lifetime. So we know that when we make a commercial baseload power plant, you have to replace those interior components, probably every year, every 2 years, something like that. So how do you get out something inside? It's easy. It's a tree ring problem. You've got a thing inside like this, and then you've got a whole bunch of things linked outside. You can't do it because it's linked tree rings. So what you do is you cut apart the interior components, and you bring them all out in between these fixed blue coils like this. This is building a ship in a bottle. Or to people in fission, it's like assembling fuel rods inside of a reactor. It's bananas engineering, because you're actually having to put together nuclear components inside the reactor. This is actually what you do, in fact, what we have in our design, in fact, at MIT. With copper, you can imagine actually, oh, well, let's not do that. Let's actually take off this top bit of the coil. We lift off that top. If we lift off all the tops around in the toroid, then in fact, I can remove the interior components in a single lift. I don't have to take them all apart. And I so much obviously love this. And in fact, that's why we design many of our copper experiments. So our bright fusion students realized that, well, look at that thing. In fact, you can actually solder that together, those tapes, and it makes a superconducting coil. And what happens is that you get a really small resistance from one to the next. And because of that, what it means is that you can actually now imagine, in fact, this is a demount, the one they made in the lab is demountable, because you can take it apart, which you can't do with standard superconductors. So that's actually what we did. We take it apart. And it looks kind of like a Russian doll, if you want to think of it that way. Is that what we can do, this is ARC, is you can actually take off the top part of the demountable coils, and you lift that off, so that now the only thing that you ever replace is a single modular unit that you actually put in as a single object. And this is small, this thing. It's only 4 cubic meters of solid material. That's the only replaceable component in the device over its lifetime. So how do you do this? And I'll get more to the benefits of that. Is that one of the ways, and this is actually a PhD thesis, it's sort of a really clever ideas about how you put together superconducting coils with joints. And so this is one way to do it, which was basically, so this green bit is the part you're going to lift off. And so we're going to get and what he's done is actually separated the place where the coils link mechanically. And what he does is he brings out, which you will be recognized from electronics, jumpers. You bring out the conductors and jumpers, which are actually then joined across on the top and over here on the side. And then you separate the electrical and mechanical joints in the thing. So where does this lead to? So where this leads to is you get these plates are put together, you compress them together, and you get very, very low resistance from one to the next. And you basically push these together. This is now, at this point, still a conceptual design that was part of a PhD thesis. You basically preload these joints, hold them together. This gives you low enough resistance to, in fact, tolerate the heating which is in there. So this is where I want to show you is to get to this, is that you actually don't need to build a huge fusion device to do this science. You can build laboratory scale experiments. And what this is showing is actually taking 80 of those tapes I showed you. You got an 80 tapes over there. You put them together in a small piece of copper, you solder it in, you press them together, and you measure the resistance from one joint to the next. And so in the end, what happens is, which you can sort of, and you do this at liquid nitrogen temperature, you actually end up with a resistance which is approaching basically only 100 nano-ohms of resistance from joint to joint. So if you do the you go through the calculation of this, is absolutely fine, actually, for a net energy system. So that what we can imagine now is actually, it's not really in some sense a pure superconducting coil. It's got bits in it which actually have small amounts of resistance, but we gain now the benefit of being able to take it apart. So why do we love this? We love this because if you were really, so I think one of the questions was, what is the thing that makes you think really that fusion energy is not going to work? And I would say without this design, it's easy. It's the blanket. It's the nuclear engineering of the things that actually capture those neutron energies and actually get net electricity out of the system. And why is that? Well, it's because in this scheme like this, you actually have to have a vacuum to hold the plasma. This has to become a lifetime component because it can never be replaced. So this means that you hang segmented nuclear components off of this vacuum vessel on the outside. And what happens, the neutrons come in and damage this. You actually have to assemble this inside of a vacuum, and it's actually assembled in parts. The other problem is that if you actually happen to not quite align the two together, the neutrons will just stream right out and actually damage the components outside. We don't like this. And in fact, this is what the contemporary designs of these blankets look like. To a nuclear engineer, these look nightmarish because it's already a very complicated environment. The neutron environment and the neutrons is very damaging to materials, and these are really, really complex. So as one of the crusty fission engineers, who I won't say who it is, one of the crusty fission engineers when I came to MIT, we sat together at the first faculty meeting, faculty dinner. He said, "What do you work on?" "I work on fusion. It's never going to work." And I said, "Well, we got some ideas. The blanket, it will never work." And I actually believe that guy. I'm not sure that blanket will actually ever work. So what do? We get rid of it, actually, because we don't need it anymore. What we do is we build, in some sense, the idealized fusion nuclear engineering system. The only reason that we need a vacuum in there is because of the plasma. Because the plasma, remember, it has basically no particles. It has to be in a vacuum. So you put the vacuum vessel right up beside the plasma. And then you basically fill the rest of it with liquid. It's as simple as you can imagine, but in fact it was come up by the students while we were sitting on Science Friday in their office one day. Said, "Well, we're thinking about all the things we're going to hang off of that vessel." They said, "Why hang anything off? Just fill it up with a liquid." So why do we like this? Because it operates at atmospheric pressure. It has no gaps by definition because it fills up as a liquid. Has no damage limits, and it's extremely effective in moderation, breeding, and a heat sink. And you say, why do I say this with such great certainty? It's because we've got 400 of them around the world already. They're called fission reactors. It's exactly what a fission reactor is. It's basically neutron sources in a pool of water, okay? So what does this all look like? This is actually what it looks like in the design. There's the plasma up close. There's the support for it. You basically bring this in. And and what you end up doing to get energy out of the system, you flow in the liquid blanket. Out it comes at the top. You've got low pressure single phase flow. It's just an enormous simplification. In fact, groundbreaking really for about how you're considering about how doing the nuclear engineering in the device. And what we use is actually a high temperature molten salt for that fluid. You could actually use a variety of different ones, but this gives you very high thermal efficiency. It guarantees single phase flow. You'll notice that if anybody has seen companies like Transatomic and other advanced fission ones, they actually use FLIBE as well too. It's got lithium in it. Lithium is beautiful because lithium is the thing that you use to actually breed the fuel in this thing. So where we end up is it actually makes 14% more fuel than it consumes, which is, by the way, that's true. It's just because you're consuming lithium at a faster rate than the deuterium. And what this means is that that's actually what you need to start the next fusion device. It has very high thermal efficiency, and you can actually shield the coils very effectively for over 10-year full power year lifetime in this. So what's the next part of this? In fact, this is the next design class. We took this another step further. How would we construct this thing? This is basically a hollow shell. In fact, it's interesting. It's actually buoyant inside of this tank of liquid. So what we're now going to do is actually look at the next feature of this, which is basically dealing with our wild success in this. It's making large amounts of fusion power in a small object, which we love for economic reasons. So how do you get the power out? We're basically going to pump the flybe around inside of this internal vacuum vessel and 3D print it. Because this is exactly what 3D printing was made for. What you want is it's not a big heavy object, but what it is an object that's got a lot of cooling channels winding its way through. So you can make, in fact, arbitrary shape internal cooling channels, which in fact greatly enhance, in fact, the heat removal. And in fact, that's actually exactly how they made the 3D printed SpaceX rocket nozzle. So we were getting inspiration from then too. And here we go. Here's the next. Whoops, there they are. In fact, I just took this picture a little while ago. There's my dog. Forgot about him. And so here's, in fact, our next set of about a dozen very enthusiastic MIT graduate students. That's Brandon, who's actually the lead author on the previous design class. Okay, they keep coming back. And in fact, 2 engineers from Mitsubishi Electric, because they're so interested in what we're doing about advanced cooling methods that they've actually joined our design team. So what is this? So let's get to about, so does this really lead to fusion energy? So we have to sort of first start about where we are compared to history. And this comes about what is this competitive fusion energy? This comes to cost. So if you look at this, so this is the overnight cost estimate of the number of dollars per watt, okay? And so mature fission plants, and in fact most energy sources are sort of down in this range in here. They're sort of $4 or $6 a watt. It depends on which technology you're talking about. Mature fission is actually there. Fission pilot plant was actually up there because the first one you build is never economically as good as all the ones you build after. We're there. And that actually, I was really surprised by this, that we even got close, in fact, to a shipping, to the shipping port. ITER is up there. And that's actually just simply the magnetic field strength, actually, of that. So our objective in this is actually then to get to that. So what does this all look like? So is it really affordable? So this is work in progress now. As I said, we went through this. We went through all the details of how you make this continuous net electricity, about 200 to 250 million watts. It's actually a nice sort of modular size to put on the grid. And if you actually just look at the costs, in fact, of the magnets and the tapes that you just sent around, and the blanket vacuum vessel, if you just take a look at those material costs, this is between $1.4 and $1.8 per watt. So this gives me a reason to believe that this is actually a place that we can go. The problem is that we know that if we base it on historical evidence of putting together these first-of-a-kind devices, this costs more like $5 billion. And that leads to $20 a watt. So in fact, where we are right now is the key question really to fusion economics. Because you notice we put features into this, is modular design and modern manufacturing can really get down to actually making the total magnet cost much more like it is in other standard manufacturing techniques. It's sort of like a 2-fold multiplier, not a 10-fold multiplier. So that's actually what we're starting to do, because we start to build real coils. So there we go. Again, the 2 guys in the garage, we were basically starting to build large bore coils at the PSFC. These things are real. This took basically 2 PSFC engineers and partial time, because I can only pay them partial time right now. They put this together. That's actually the magnet is sitting over here in the cryostat, and this is a magnetic thing, and you can see that it's being pinned because it's being pulled out in midair actually by the strength of the magnetic field. The very first test of it actually surpassed the ITER's magnetic field. It's just like, okay, this is really brand new. This is things you can innovate on very fast. Oh, by the way, I just found out just before I left, they actually failed the coil actually for the first time, and it actually survived. And we're learning that right now. It's because we can take this apart and put it back together in days, not years. Right? So there's the other part. That now we're getting to the place where we can see a pathway to make this technology development small enough that we can start using what I would call, we can do this with private funding and actually base it on what I call startup attitude in this. So here we were before. This is the plot I showed you. ITER has no choice. It actually had to be there. So what we've done is opened up this space, because this is the magnetic field strength along the horizontal axis. We've opened up this space, actually, with this new superconducting technology. And what this means is that if you go down along this curve of constant gain, arc resides right here. Because I can tell you, is most of the design work in this was to make it that small. It's hard, because those neutrons want to go long distances in the materials. You have to shield the outer side materials. And we think that we've actually, based on our knowledge of this, we've pushed this as far as we can get. But there's another place you can go. Is that, well, the reason that you can't go below this line is actually because you can't shield it for very long. But what if we don't try to make continuous long-range electricity? Let's make something that, in fact, sparks the fusion revolution. Thus comes the name, right? So I'll get back to that. The other thing that's changed is that MIT has become very serious about climate change, about the energy, about low-carbon energy centers, low-carbon energy research. This is, you probably got the emails of this as a plan on climate change. What is in this is a very important commitment of MIT to orient its energy initiative to looking at 8 interlinked low-carbon energy centers. Where is this in? Solar, energy storage, materials, carbon capture, nuclear energy, which is fission. And I almost fell off my chair when they told me this. They're actually committing to fusion. And what they're saying is that they're basically pledging to raise through the private sector $8 million a year, funded through a consortium, actually, to in fact support this work. So where does this all lead? So we've changed so here is affordable, robust, compact, smaller or sooner. We're not sure which one is the right one. There's a fight going on about who came up with one. Privately funded ARC, Spark. And the idea in this is very interesting. I mean, if you saw that and you say, look, we've got this model about making electricity. We want to get there. We've got an economic model that looks like we could get there. It's all very viable, but it's still too big for the first step. So if this is put in front of you, say, build me the smallest thing that shows the most essential part of this. And that's actually what Spark is. What it is, it's a combination of the ideas of the magnet technology and other things in ARC, and it combines it with the fact that we've built 3 toroid already at MIT of that magnetic field strength. But now we make it with the new superconductor. And what this allows us to do without bringing down the electrical grid of Boston is actually make net fusion energy gain in a very small device. So that's actually what it does. So what is it? So how small is it? Well, the first part of anything is how you can it's small enough so you can sell it. And we actually think, because this is going down to 5% of the volume of ARC, it's actually in the hundreds of $1 million range, which is actually within reach, in fact, of private funding. In fact, this has been raised in private fusion funding. We can cite it at MIT, and what this actually does is achieve deuterium-tritium gain with basically exactly the same physics that you saw in that discharge that started the talk, in a very small device that we can actually cite it at MIT. And I would encourage you, in fact, this is being driven to a large extent by our young scientists. They're waking up as old guys about what's happening out in the real world. And in fact, in some sense, in the world that's out here, about this rapid cycle of innovation. It's not waiting around 40 years for the perfect thing that will never come. We have to start doing things now, actually, to make this work. And I would encourage you to, in fact, all you have to do is Google Spark, Highfield and MIT and all this. These are all postdocs and graduate students. And I can't do as good a job as they can, but basically what we're doing is saying we're waking up to a new technology cycle strategy. And here they are, in fact, standing in front of our Highfield torus, right there. Yep. So this is what we're moving towards, and the way, just to say, is that because we've got now this young set of scientists, we've got an energy mission, not just a science mission. What I would say, we're adapting what I like to call an academic startup attitude in this. And so where does this all lead? So Spark, we believe, ignites, and the puns are intentional, a rapid development to fusion electricity. Because we can see now a pathway to this which is so attractive, but we can't let the single size unit size of this get in the way of the parallel developments that actually take you there. And we believe we actually have a model, which we can do actually at MIT scale devices, in fact, to do this, of answering the multitude of questions which actually get you, in fact, to ARC. So that's what I would say, is that please come join us actually in this endeavor. there's a whole host. What I'm excited about this is not just the fact that there's another source of funding that can come into fusion. It's a dialogue with a much broader audience about these new kinds of technologies, about where they can take us, and about making fusion happen sooner. And when I see come join us, I also mean please come see us. If you are in the Boston area, I'd be more than happy to show you all of this stuff. It's sitting in our labs. And now, as I say, in some sense, the closing one is why now and why at MIT. And really, in a way, I'm seeing a convergence of sets of needs and capabilities that are coming together at the same time. So first of all, we've got this high magnetic field torus. We've built them, and we've established the fusion science of this. Now we've combined this with vibrant, innovative young researchers. We have now a new capability of REBCO technology and fusion magnet expertise, which we have at MIT. Not to mention, we basically have a mini national lab at MIT on Albany Street. It's got 150,000 square feet of nuclear research space. And now we combine this with MIT's new commitment, in fact, to low-carbon fusion energy. And we believe this actually leads you to spark. So there we go. Thank you for your attention. Really appreciate it. Oh, and by the way, I swear we came up with the acronym before I knew anything about that we were giving a talk at PARC. P-A-R-C. So thus Spark in the Park or whatever. Which I have to give credit to my 18-year-old daughter who pointed out this completely obvious thing to me, which was flying over my head. Yeah. Oh, want to be over there? Sure.
Yeah. Wow. Wow. What a great pitch deck.
I'd like feedback on that too, please.
That's our term here in Silicon Valley for an entrepreneur that wants to raise money. And so what the financial community looks for is a big market. Certainly have that. Technology breakthrough. Wow, phenomenal. Down the road in terms of proof of concept, lots of stuff is working.
Yeah.
Great team, great leadership. Those are the four big ones that they look for, and then. So then the next question is, how much you're trying to raise, and you put that up there, right? So then the next question is, what are your expectations about pre-money valuation and terms and all that?
I think I better go take a finance course.
Yeah. Okay. So Q&A time. So we had a bunch of pre-submitted questions. So maybe I'll go through some of those first. And then we have a microphone that will wander around and ask some more. So you may have covered this. Discuss the expected lifetime of the vessel and radioactive materials disposal.
Yeah. So we've designed. So it's one of the. Would you mind putting the presentation back, because I actually have because I saw these questions before I had a quick answer to that. Oops, what happened? Yeah. So. The component lifetime. So this is actually one of the features of the new design, is that what we're looking at actually is that this component in here, I know I wasn't supposed to walk in front of the screen, but this component in here, inside of here, is what's the replaceable component. And because you can go, it's a neutronics lesson, which I'm not going to go into, but you basically can get down the damage rates in this such that it can, with fairly known steels actually, can be replaced probably every year or so. But I would point out is that it's built to be replaced. I mean, that's the whole point of it. It's built as a singular modular unit that you replace and put in another one. In terms of the total solid waste, this ends up to be about 4 cubic meters of material. And in fact, the goal of our present design class is actually to take a look at both reduced activation steels and it really comes down to there's no radioactive waste in the normal sense. It's just activation products that are in the steel. So first of all, we reduced that by huge amounts by getting rid of the solid blanket. And we believe that we can actually get this to decade timescale shallow burial, actually. And it's a very small amount of material. So that's the other part. So I think that answers those questions. Yeah.
What are your perspectives on the leading private fusion efforts like Tri-Alpha, General Fusion, Helion, and so forth? Yeah.
So I'm actually very supportive of those efforts, and I sort of have a simple way of, in some sense, of talking about what they're doing. So the startups in general are looking for a new way to skin the cat about how you get that confinement. Those things that I told you about are basic sort of laws of physics, okay? So are there ways that you could, at much smaller scale with much less complex technology, actually get you to a place where you can meet those criteria? And companies like Lockheed Martin, General Fusion, Tri-Alpha, what they're doing is taking those, building them at smaller scale, and in some sense assuming larger science risk because their schemes are not so proven. But that's okay by me because it's like they're rapidly innovating. The way I would say that we're doing is that we're putting the risk on the technology, and we're actually using known science. But both of these pathways are actually mutually beneficial to one another because they both feature more rapid turnaround cycles. And I favor the left one for the simple fact that maybe 5 years ago I would have favored the right one. But I favor the left one because I see already how fast the technology is in fact developing. And it's a judgment call in a sense, but I think both of the approaches are actually interesting. Yeah.
So maybe we'll ask for some questions from the audience. So there's a microphone here.
If you can only run 10 seconds each run, what's the frequency you can run, like a cycle time?
Oh, so for Spark you meant?
Yeah.
Yeah, for Spark. So Spark is intentionally made to not run continuously. This just comes from neutron physics, that you can't actually shield the magnets at something which is that small. So so where that ends up, in fact, it's a design challenge in Spark about how you get rid of the heat, actually, which is coming up. What I say, dealing with your vast success, because you're making so many fusion neutrons that you're heating up the exterior components. I'm very happy about that, actually. So where that ends up is that we actually have a set of technical options that we're looking at for actually the cooling options inside the coils, which are greatly benefited, by the way, which I didn't get a chance to talk, by moving away from liquid helium. These do not use liquid helium cooling. And this is another big aspect of why these are so attractive. We believe we'll move to liquid neon cooling or liquid hydrogen cooling, actually, in these.
Also, the good news is that the size is very close to ours, like a PVD system, half Tesla, about 2 or 3 meter high. But we do worry about our life because how do you shield the neutron? What's the protection needed to do this?
No, that actually has to be put into a shielded vault, like we put the other ones into. I mean, Alcator, the high field one, is making lots of fusion neutrons. So I mean, you put it into the usual containment system, but it's just a meter or so of concrete, but that shields you well enough, just like it does from a fission reactor.
I see.
Yeah.
Okay. It's a very good talk. In fact, there's no data you realized, but it's very good.
There's no what?
There's no data in your presentation, from your project. So
I actually have data about the budget.
Okay. Exactly.
If you're interested to know about the budget levels, I can tell you about that.
The data's in the problem set. Yeah, so maybe this
Well,
one here.
there is a budget. It's what MIT's president told me my budget is, okay?
I'm sorry, I just didn't catch how you get power to the grid. Do the neutrons heat the salt blanket, and that goes to a steam plant?
Yeah, sorry if I skipped over that. That's exactly what it is. So so in the end, so what happens? And by the way, this is one of the reasons you like DT fusion is because in ARC the neutrons are, to your question, the neutrons are shielded actually from getting outside because it becomes thick enough actually that it thermalizes all of the neutrons. So that's actually what's happening is that the DT fusion neutrons are coming out. They're basically thermally they're giving up their energy to this blanket. The blanket operates already at high temperatures, and of course it increases the temperature of that. You either extract that flow out through a pipe actually and send it through a heat exchanger, or you would put the heat exchanger inside the tank so that you don't actually have to flow the molten salt through at a very rapid rate. I think the heat exchanger one's probably the best. So that's actually how you get energy, and in fact, it's basically how you get energy out in any standard fission power plant. You're circulating both the coolant. That's that we like this so much. The coolant and the moderator are the same thing, and they're just going through. Yeah.
So let's take one from over here.
Livermore Labs experimented with another geometry, the tandem mirror.
Yes.
Very much like a laser cavity with a mirror at each end. It would similarly benefit from increases in magnetic strength. And
Absolutely.
have you looked at that and any implications?
Yeah, so in fact, so one thing to realize about this, in fact, where was it? I had it. Actually, there was some budgets you want to see. This is the reason that we talk about Spark as a tokamak is not because I even personally believe the tokamak is actually the right option for eventually the best option for a commercial power plant. That should be decided, well, in some sense, by the marketplace, of course. But because we're not there. I mean, the problem is we're sort of dreaming about these things. We need several versions. We need several different versions of these all working so we can figure out what is the best one actually to go forward. It's sort of like everyone is assuming, when the Wright Flyer took off, we all prefer 737s versus Dreamliners. I mean, it's bananas. I mean, there's no way. They have the data in hand to do this. So what is great about this technology development? It's agnostic to all of anything that uses magnetic fields to confine. So this includes spherical tokamak, and in fact, Princeton and ourselves, the Princeton Plasma Physics Lab and ourselves are looking, in fact, at what this new technology means to the spherical tokamak, which they're exploring. Stellarators, which are another way to basically make that toroidal magnetic field, could be greatly changed. The tri-alpha technique, which some of you might have heard of, which is the field reverse configuration. I'm going there tomorrow because they're interested about this new magnetic field technology. And yes, mirrors, the one that you mentioned. So in fact, there's gas dynamic trap. There's some very interesting results coming out of Russia, which shows this might be really interesting as a neutron source, if not a big net energy gain. So anything that uses magnets to confine the plasma is revolutionized by this, because you can go to this different place. Yeah. And a whole host of other technologies, by the way, not just in fusion.
So someone else. So let's go in the back.
So the joke about fusion's always been it's 50 years away.
And it always will be.
Okay, so can you?
I hate that joke.
Okay.
I'm really trying to get that joke out of the English language.
It also applies to gallium arsenide.
So what? Can you revise the joke?
Yes. Well, I mean, you're right. And in a way, that's my, so we're in a way you have to watch out when those jokes become almost realities to yourselves. Then you start getting into this attitude almost. Well, it's okay if we wait, another 30 years for something to come along. I'm like, no, I'm sorry. Okay, and it's not just because I'm getting old and I want fusion to work before. It's just like I work a lot actually with the MIT climate scientists now. Particularly after becoming nuclear engineering department head, we can't mess around. We need low carbon energy solutions like now, not 30 years from now, now. In fact, this is even too slow for me. It's just resource limited. So I would say is that I can't know, in fact, that this will work for sure. But I cannot stand the fact that we won't know that it won't work, okay, on a fast enough time scale. That's what we have to do. We have to get the time scale so that we fail and succeed on a much faster turnaround cycle. And that's actually what we think this does. It actually gets us to sort of several year turnaround cycle, not decades.
So if it were all green lights,
Yeah.
how long would it take and what are the barriers? Is it more engineers, more money, or more open, or are there unanswered design questions?
Yeah. Oh, there are certainly. I mean, to get to Spark is. Let me start. So yes to all those. We're undermanned. It's. But we have a great core of a crew, but we need more people. We need more students, and then we have to concentrate on the key. What we actually have to figure out is, in fact, the right sets of steps that actually answer the key questions as we go on. We're not quite there yet. We've answered a lot of the things we think, but we know about how to get there. But again, I think the answer to that will lie in the results themselves. So, one of our cartoons of this is that the very first thing you need to do in a time span of a few years is actually go from those small model coils to actually building, tabletop coils that actually demonstrate all these things, the demountability, the high magnetic field. And that's very attractive, actually, because not only, by the way, are you advancing fusion science, but you actually impact things like MRR science, compact cyclotrons for for cancer treatments. You start impacting a whole bunch of other fields. So I want to do that, and then the idea is that you would take the lessons that you learn from that engineering, and then you build Spark. You learn about what happens in Spark, and then you build up on that, and it gets muddier the further out you go, because it's like any technology development. I mean, we can write out some of the aspects of the challenges about how you get to those things, but until you speed it up and get more answers, you're not sure. This part here, we have a very solid plan for. We have a very solid plan, and I think probably in 2 to 3 years, with the right resources in the door, we can make those magnetic field coils. I don't think we have no doubt about that.
Yeah, so it's the known unknowns and the unknown unknowns.
It's
peeling back the layers of the onion.
And it's the other part about the things I will insist on, small and modular, because fusion is complex. So when you can make it small and you can make it adapt quickly, you start reaching that condition of fast failure, fast success, and that's actually what we need to do the most.
You think 10 years and 300 million?
Yep.
That's pretty good. Yeah.
Particularly if we can site it at MIT, and we're
Cheaper
working
than
on
here.
that actually.
It's less expensive than here.
Yeah. No, it's an aspect of keeping it local, and so there are barriers to that as well too. Regulatory issues and things are not regular. I mean, you just have to work through those things. But I think if we've got the will of MIT behind us, which I think we do, then we can actually see our way through those.
So over there.
I'm just going to grab a water.
So I think I missed something. We 100 million Kelvin in the middle, and we have molten salt on the outside. And you seem to imply that there's 77 Kelvin around this coil.
So let me go back to the little diagram. Yeah. Well, 100 million Kelvin is insulated by the magnetic field.
Right.
And so the thermal engineering aspect of this is that what happens is that so the tank itself, in fact, the way that it works is that the tank and this are actually preheated, because the salt is only liquid actually above 450 C. So then you bring in the liquid, and then it heats. Then actually on the outside of this is actually you have a insulating barrier, and on the outside of this water cooling. I didn't show it. It's not in those cartoons that I showed, but those are built into the.
Where's the 77 Kelvin in here?
77 Kelvin is actually well, it's actually 25 Kelvin. Is
Okay.
actually then in the coil, which is out that, and
It's outside of
it's
this.
outside
okay.
of that. Yep.
Okay, got it.
Yep. So it is pretty cool that you go from 25 degrees above absolute zero to 100 million degrees in about yeah. But it's actually, we actually do it. In fact, in Alcator, we actually have a liquid helium cooled pump that sits in the diverter. So it's actually 20 centimeters away from 100 million degrees. Wow. That's how amazing the insulation of magnetic field is. Yeah.
Very hot. And then far back.
Is there any indication that the current density of superconductors will continue to increase?
Yes. In fact, that plot that I was showing was the current density at high magnetic fields of the superconductor is being improved by the fact that they're starting to understand better about how to do flux pinning. If you know about superconducting, that's basically about what keeps it from not being a superconductor at high magnetic fields. So that performance has improved a lot. And in fact, by our estimates, I think we overestimated the cost of the tapes in ARC by a factor of 2 to 3 already, because the tapes have gotten that much better.
All right, thank you.
And it's still evolving. Yeah.
Okay, so right down here. Can you comment? Here's Oh, yeah. So the question was,
I'm against
what's your view
coal.
of cold fusion?
No, I'm just
And-
cold fusion. I have no strong views on this. I mean, it's some people look at it and they believe that there's small net heat which is produced actually out of the systems, but as far as I know, there's been no evidence of that this is caused by nuclear reactions. So I don't have any strong comment. We're making 100 trillion fusion seconds a second. I know that for sure, with multiple diagnostics.
Go ahead.
I'm curious, for a full-scale device, the ARC device that you talked about, in an operational setting, what are the anticipated failure modes?
Great question. Yeah. So there's the things that actually, so if I was to say right now, the highest probability of the failure modes is power excursions on the inside of this. In the end, what you're doing in these kinds of fusion is that the 20% of the power that is used of the fusion reaction that is used to heat the plasma means it comes out as plasma. And that plasma tends to concentrate in very small areas. So what happens is that you end up with surface areas which have heat fluxes which are approaching that of putting materials on the surface of the sun. So yes, that's hard to get that heat exhaust out. So that's probably the biggest our concern. That's actually why the next design class, that is, I'm going to miss their class tomorrow, they're working actually on building margin into that by in fact coming up with some of what I showed, innovative ways to actually get out the heat flux at a higher rate using this sort of new topology that we've got with the liquid flibe and this rather thin channel. So it's that. And then the other part is because when those fail, that almost means that for sure the plasma will fail. That's actually what makes plasma or fusion so safe. It's a vacuum. So literally, if you were to go like that into ARC, it would stop it. Easily stop it, actually. So it's very intolerant to any materials falling into it, and that's actually the thing that would stop it. And when that happens, then you would have to restart it, and then you worry about those aspects of it. So that's probably the biggest challenge, I think, actually in an operational sense.
Along those lines, could you comment on how much radioactive waste is created and how long-lived it is, and what are the safety issues?
So that's actually that's work in progress because it depends greatly on the details of the specifics of the kinds of steel that you put in that vacuum vessel. So I don't have an exact quantitative answer to that because there is no single answer. And the good news is that, I mean, this is why you like fusion. If you're worried about the fuel cycle aspects, namely the radioactive waste that comes from fission, you can do things to ameliorate this, but you can never avoid it. It's because the fission products are part of what makes the energy, and that's what happens when it splits apart, and it makes these, and it makes other actinides. In fusion, you can engineer your way out of this. Because there's no physics that actually tells you can't build the surrounding materials such that they can be very, very low activation. It's just engineering, quote unquote, just engineering. Yeah. And actually, that's why we're working on innovative engineering aspects to get at that problem. So
maybe this one here. You got your hand up quick. So he's got a mic.
Hi. My question is related to the risk question is, say, what is the maximum possible risk, assuming you had like a nefarious operator of one of these?
yeah.
What's the maximum conceivable?
Yes. So okay. So I'll just start with the basics. So fusion can't melt down because there's no chain reaction. I mean, the standard way that you think of a fission reactor melting down. The other part is that there's essentially no fuel inside the device. So this means that when you have accidents that leave the energy content of the fuel sitting inside of it can't really happen in fusion. The other part is that it has to happen at 100 million degrees. So this means that when things go wrong, like I said, like blowing on it, it stops. Okay. Now there are some other issues, namely that you do make activated materials around, so you have to contain them in something. It's actually why we like this design, is that this actually this one rather simple tank, actually, that holds this molten salt is in fact this becomes the equivalent of it's not quite that, of a pressure vessel in a standard fission power plant. This becomes the safety boundary, because all of the things that you're concerned about are the radioactive materials inside of this boundary. And even then, it's like, so, you know, that's the greatest risk, I guess, is that containment being broken. Would be I guess. So proliferation risk, right? So the proliferation is in fission is always, again, you can't avoid some aspect of proliferation risk in fission. And the simple reason for this is that the things that you do to make fission work are also the things that you do to make nuclear grade weapons materials. It's just the physics is the same thing, enrichment and so forth. In fusion, what happens is that there's absolutely no requirement for fissile materials anywhere in this thing. So if you sell this to somebody and you're worried about them using the neutrons to make something with it, the moment they put in something that is not right, you know this right away. And they can't say, I'm putting this in for reasons that I like, you know, because I want to make energy. No, you're putting this in because you want to make, you know, things with the neutrons. And no, you have to stop using it. So it's not zero proliferation, but it's a completely different game, actually, than what you have with fission.
In the far back.
Hi. So it seems like you're doing an amazing job managing all these really great minds, and I really want to emphasize that is not an easy task. Like giving them the correct problems, and you don't have to like acknowledge it, but I'm acknowledging the fact that that's amazing. Giving them the correct problems, kind of teaching them how to work together. These are all amazingly important things, and I think it's a real key to your success. So good job. With that said, how do you like take all of the amazing work that you're doing and take the alums and make sure that they can kind of feed back into the cycle? Like, are you placing them at places that you can collaborate with them? Because you're creating like this amazing group of people that know how to work the way that you want them to work. And each year you have more and more and more of them. Are you making it so that, or can you make it so they can continue to contribute? Okay, thanks.
Yeah, that's, you know, it's a great comment. I usually am greedy and I want to keep them all to myself to solve all of these problems. But so this is actually, you know, that's a really good point. And in fact, this is what I said too about the aspect of I really am enjoying already actually not talking just to other academics or to other fusion people, but getting out into a broader set of the community, which includes the MIT community. It's exactly the kind of engagement. And in fact, if we would have had more time, out of love and, well, in fact, some of them go out and do talk to alumni clubs actually in different places around the country. But I think what you're talking about is now, like alum and here are all involved, a lot of them involved in high-tech companies. What about, you know, how do we think about, you know, the synergies that could be involved with them, in fact, interacting with alum? It's a great idea. I hadn't really thought about any particular solution, but we'll keep that in mind. Thank you.
So you're okay for a few more?
Absolutely.
Yeah.
This is what I do for a living.
Okay, so down here in front. Justin's coming with a microphone.
So given the importance of the need to bring the technology to bear, given it is a very, I mean, it's very elegant, beautiful, I'm excited about the opportunity versus thinking it was always 50 years away. You showed that MIT's making a commitment of $8 million, I think, starting in 2017. And you look at I think we can do so much with 10 million and 100 million, et cetera. You know, you think of the scheme of things, that's not a lot of dollars relative to what gets spent in a lot of places. You have the billionaires at Paris that we will help fund. Bill Gates talks every year at TED about all the things they're doing. I mean, what's going on to try and get it faster from your side? Are people spending out of your lab to try and start companies? Is the university trying to get more money to come to bear to help you advance it? Are you partnering with Stanford or other universities to try and get a broader base?
Yeah, so pretty much yes to all of those things. In a way, it recognizes it's sort of an experiment for us, actually, about this different model about how we support and review and all the different things that you do about how you get the research going. So we're working that out. In fact, you guys are kind of like guinea pigs a little bit, because you're one of the first sets of large people that I've talked to actually since MIT announced about what they were doing. So the way I see it is that what we have to do is start small and build credibility. Because when I go out and talk about fusion around in most places, it's just like, it's to the comment again. Haven't we heard this before? I mean, this has always been, we're worried about this. We have to get back on a path that demonstrates that we're really serious about innovating and actually accelerating that development pace. That's why I think it's right to start slow. We've actually started some engagement, like I said, with another university, Princeton, in this, because we need partners. Okay, we've actually started partnerships with industrial companies. Mitsubishi Electric, in fact, as I said, pointed out, was actually being part of our design class, and they're local in Cambridge, so it's easy for them to participate. And yes, philanthropic giving, absolutely necessary. Necessary, very, very important in this. And we've actually attracted some of that as well too. And we're just growing this. It's kind of a new game for us, actually. We're just used to usually getting it all from the government, and we're changing that. Yeah. So thanks.
So over here, this first time over here.
So if someone who was an expert in the field but was skeptical of this approach were to point out where they thought the big risks were,
yep,
what would be the places that they would point to and say, this, and this are the biggest risks for this approach not working?
Yeah, so probably magnet stress is probably one of the bigger ones, because it seems feasible, but you're pushing harder on it. So that's one. I think that there's some people are skeptical about the demountable coils, because nobody's ever built demountable superconducting coils. So I think there's a natural skepticism that comes with that, and so I just want to prove them wrong by just building them. Because we're pretty sure they'll work, actually, at this point. So I would say that those would probably be the two biggest ones, which would be focused around the fact that the magnetic field is and the third one is that you can't actually shield effectively enough at small scale, because that's actually what we really want to push to, is small scale. So, but here, well, in fact, that's what we do know how to do, because that's what we do in the nuclear engineering department, neutronics. So I would say that I can blunt that criticism. So those are probably those are the three biggest ones when we bring this out into the community.
Yeah. So Manny in the far back, very far.
Hi, so I work on the NIF laser at Livermore, so it has its own issues, but I'm not quite an expert on tokamaks, but yep, it seems like you're assuming that the physics of burning plasmas is a given, that if we have this field strength, then confinement will be fine, transport will be fine, that the physics of ignition will work, and everything is in the engineering surrounding it. Yep. Could you comment what the risks of, I mean, it's unknown that we can make a burning plasma, even if you had the field strength that you want. Am I wrong in that, or is that? So, I mean, it's a relative, well, until you've done it, of course, you might always think that you might come into some surprises. But in the general feature of burning, so just to orient everyone else to what a burning plasma means. Burning plasma means it's that recycling of the heat that I talked about. So when the fusion reaction occurs, 20% of the power is released in a charged particle that actually loses its energy back into the background plasma. When you get to a gain of capital Q of 5, this means that the external power that you're putting in is actually equal to the amount of internal power. So you sort of intuitively know this can be different. It's sort of like, the analogy is holding a blowtorch to a wet log versus a raging bonfire. Those seem to be different, which is ignition versus, sub-ignition. So it's different in our fields slightly as well, too, because one of the features about what this means is that what will happen is that strong central heating in the core of the plasma will become the dominant mechanism. So in tokamaks in general, because you can go run lots and lots of experiments and simulate that in some sense, even though it's not burning itself, it tends to not really destabilize the plasma. Plasmas like power. They tend to not like, these plasmas like power, they tend to not like particles and things like that. So it's not, it's not that it's that's actually where we want to see spark, because in fact spark will get you in a very fast time scale, not just to
demonstrating to the world you can make more energy than you put in, but you actually start to see that physics. And I think that that would be, in fact, some of the key. Just like NIF, you guys are starting to see a little bit, and in fact, of the ignition in the very small hotspot, you can see there's differences, right? Because you start turning on alpha heating. I think that, Spark will start turning on alpha heating at a pretty substantial level. But I'm pretty confident, actually, that, in fact, the physics will, in fact, work out. And there's a whole, I'll get into way too many technical, we can talk offline. It turns out going to 10 Tesla is also really interesting, because if you know about alphanic problems does that make sense? Yeah, okay, so don't worry about it. It turns out you go past to some other thresholds that make the plasma more stable in a burning regime as well, too.
Is that theoretical, or is it like...
So it's somewhat theoretical, it's somewhat experimentally based. So it turns out, in general, what happens when you go to very high magnetic fields, and we've seen this over and over again in our own experiments at MIT, is that you squash down the instabilities, almost of all types, because you're going to a lower ratio of plasma pressure to stabilizing pressure, and that tends to make it a much more stable regime. And there's another critical one, which turns out is that when these energetic particles are released, they are locally actually exceed what's called the Alfvén velocity, and the Alfvén velocity is the speed at which the magnetic field's information distributes. That turns out to be unstable. You beat that by going to high magnetic field as well, too. That's getting that's getting too nerdy, actually. Probably. That's getting too many details, actually, for this.
Could you comment a little bit more about plasma-facing components?
Sure.
And what happens when you try to go to these higher densities with the higher field?
Yeah, so that was in some sense the question about like what's going to make it fail. It's actually, that's what we call generically plasma-facing components. Namely, these are the material objects that actually have to be right up on the surface of this and actually taking out this heat that gets concentrated in these particular areas. So I don't have, that is a challenge to this, but we can talk offline about this actually. It turns out we've learned some physics about this, that it turns out that very counterintuitively going to high field and small sizes actually improves this. It makes it easier actually to do. And it comes from the physics about how this boundary layer of the plasma is actually scaling with different parameters. And it turns out making it smaller and making it higher magnetic field is better, actually, for that. So we're pursuing that, but at the same time, what we're doing is not just trying to solve it with physics, but trying to build more margin into that problem that you just mentioned. And that's actually that's the design class that we're doing right now. We're taking these, you can see them in here. Actually, it's these pumps which are here. These pumps are going to take fluid from out in there and actually push them through at high pressure, in fact, through 3D printed cooling channels through here. And we think we can actually increase the peak heat loading by a lot, actually, by doing that, to improve the engineering margin on it.
So it's...
I'll come back in a year and tell you the answer to that one.
It's 10 minutes after midnight in Boston. You got time for a couple more?
I'm fine with a couple more. It depends. These guys are getting tired, but I'm happy to answer more questions, absolutely.
Okay, let's do that, yeah. Okay, so, Joe, could I have the other slide back here? Is Joe still up there? Well, coming attractions, it'll be up here in a moment. Coming attractions for the Energy and Environment series of the club. We have the Spotlight, our annual event where we highlight an outstanding person from the community that's almost sold out. There's just a few more seats left. It's a week from Saturday, right? And then we have a new event, Energy Access in Emerging Economies, and that's about microgrids in emerging economies on April 12th. So now I'd like to thank Dennis. So thank you so much. Doug went out and got, I hope you like red wine. Doug went out and got this fantastic Camus Vineyards, 40 years, and here you go.
Well,
Thank you so much.
Thank you very much, and thank you for all your attention in coming to us.
And